welcome back to another video. Today we're going to be doing numerical integration 4. So first off, quick review. Every function corresponds to a curve. So for instance, if we had function f of x, you could draw that as something like that. Or f of x equals x, my bad. If we have, say, f of x equals 1 over x, then the graph would look something like that. For one more example, if we had f of x sine of x, f of x equals the sine of x, then the graph would look something like this. I'll go back to the line. Now, in all of these cases, if we were to add these to a definite integral, say the integral of 0 to 1 x dx, definite integrals are integrals that correspond to the area under a curve. So if we had an integral like this, and we were to draw this out, we have the same function as before, but instead from 0 to 1, we know that this integral is corresponding to all of this area right here. If we do it with our other example of the integral of 0 to 1 over x dx, we can draw our graph like the other ones. And again, from 0 to 1, it would be all of this area right here. And if we have, say, the integral of 0 to 1 in our last example, sine of x dx, we can draw our graph from 0 to 1. It'd look something, say, like this. Now, these integrals can be computed numerically. If we were to use our first example, I'm going to redraw the graph. Actually, I'm going to redraw all of these real quick. Alright. In all of these examples, from 0 to 1, we can compute how much each bit is by using little rectangles. And you see, we can build these rectangles up, and we can generally find out this area. Now, it isn't going to be exact, since there is a little bit of the tip of the rectangle still showing, but we could generally figure out what all of this is by adding the sums of those rectangles. Likewise, we could do the same for this one. Now, the more rectangles you add in the given curve, the closer your approximation is going to be. Since, even though there are more rectangles, and you would think that would be a larger margin of error due to these, if there were more rectangles, say, like, if we were to go back to this one over here, if we had less rectangles, it would look something like this. And as you can see, this is a lot smaller margin of error than this. It just takes a little longer to compute. Finally, to our last example, the boxes could look something like that. And we can shade all these in. Alright. Now, to find the area under these curves, we can use formulas. So if we go back to our first example, let me fix my camera real quick. If we go back to our first example, we have the integral of 0 to 1 x dx. We know that in this case, we can compute this by having x squared over 2, bar 0 to 1. We can replace 0 with 1 with x, so we have 1 squared over 2 minus 0 squared over 2, which is 1/2. For our other one, we have the integral of 0 to 1 over x dx, which equates to, if you guys know this from some of our previous videos, the natural log of x, bar 0 to 1, which we can equivalent to the natural log of 1 minus the natural log of 0. which is 0 minus infinity, which is just infinity. I'm also very bad at drawing infinity. And lastly, we have 0 to 1 sine of x dx. This, if we differentiate, would be negative minus cosine of x bar 0 to 1, which we can rewrite as negative cosine 1 minus the negative cosine of 0, which is, if we simplify this down, negative cosine of 1 plus 1, since the cosine of 0 is 1. Now, the fact that we can use these formulas is known as the fundamental theorem of calculus, one of the greatest theorems in all of mathematics. Now, we can actually extend this topic to double integrals. So if we were to have something like, say, f of xy equals x squared plus 2xy plus y squared, what we can do, we can have a double integral from 0 to 1, f of xy dx dy. Now, what this means is if we were to draw a three-dimensional graph, that's pretty bad, let me fix that, and we were to add a cube onto that graph, what it would mean is it would be the volume of this cube. So it would be anything below this surface. So I can map this out here. Oh, too far. My bad. Like so. And we have that volume. So now let's do a quick numerical example. Here's what we can do. If we have our function f of x equals x squared, then that would be the integral of 0 to 1 x squared dx, or the integral of 0 to 1 f of x dx. And what we can do is if we were to draw this out, it would look something like this. We would have the upward graph, and we could have our boxes, or our rectangles, so we could figure out the area under this curve. Now, each one of these, we can divide this, since the rectangles are all even width, we can divide this into n equal parts. So this line is 1 over n, this line is 2 over n, this one is 3 over n, so on and so forth until we get to k over n. Now what we can do is to find this, what we can do is we can rewrite it as this. We have the integral of 0 to 1 f of x dx equals the limit from n to infinity n over k equals 1 f k over n minus 1 over n, like so. We can simplify this. Since it's f of x squared, we can square this. So we're left with the limit of n to infinity, n k equals 1, k over n squared minus 1 over n. Square both of these, so we have limit from n to infinity, n k equals 1. We have k squared over n squared minus 1 over n. Now what we're going to do is we're going to take all of the n's and we're going to move them to the front. So it becomes the limit of n to infinity, 1 over n cubed, since there's 3 n's, n k equals 1, k squared, since there's 3 n's. Now, if you know from my previous video, this is the sum of all numbers squared. So we can rewrite this as the limit of n to infinity, 1 over n cubed. And then we can just replace this entire thing with a bracket 1 squared plus 2 squared plus 3 squared dot 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 all the way to n squared. Now again, if you'll remember from our previous video, we can rewrite that as a formula. We can rewrite this as 2n plus 1 over 3 times n plus 1 over 2. And this is the sum of any n squared numbers. So again, if we were to try to find the sum of all square numbers up to, say, 8 squared, we could plug 8 into this formula, and that's what we get. Now we're going to bring out these over 3 and over 2's. So we have 1/6 the limit of n to infinity, 1 over n cubed. Then we just write it with that. So we have 2n plus 1 times n plus 1. Simple as that. Close bracket. Now what we can do is we can multiply all of this together, and this is going to look a little confusing, or it might, I don't know. We have n cubed, 1 over n cubed. Then we have 2n cubed plus 2n squared plus n squared plus n. We could if we multiply all of this, we can replace it with this. Get a page real quick. So now what we're going to do is you remember that n cubed, 1 over n cubed we had right here? We're going to distribute that to everything. So it's going to be 1/6 limit from n to infinity. And then we're just going to divide everything by n cubed. So it's 2n cubed over n cubed plus 2n squared over n cubed plus n squared over n cubed plus n over n cubed, close bracket. Now we cancel. So again, we have 1/6 the limit from n to infinity. We divide it all. So we have 2 plus 2 over n plus 1 over n plus 1 over n squared, since the n's would equal 1. Now here's where it gets a little tricky. Now we're going to use this limit here. Now if n were to keep getting bigger and bigger and bigger and bigger, these fractions would eventually get smaller until the point when it reaches 0. That's when n would be infinity. So what we can do here is we can rewrite this entire thing as 1/6 times 2 plus 0 plus 0 plus 0. Since all of these eventually, at some point, will equal 0, and we can generalize that with the limit, which if we multiply this all together is 1/3. Now, there was a simpler way to do this. I'm just showing this out in the video, but what we could have done instead, so the integral of 0 to 1 x squared dx, rewrite our problem, we could have simply factored it the way we normally would, x cubed over 3, bar 0 to 1, which is equal to 1 cubed over 3 minus 0 cubed over 3, which is 1/3. And that's how we can use this. Thank you very much for watching this video, and I'll see you for another one. Bye.